Hello everyone and welcome to my presentation. So today I would like to talk about the control of microstructure on an iron-based shape memory alloy fabricated by laser powder. So with the presentation I will start with a very short introduction about the motivation of this work, so why we are performing this type of study. Then I will continue with some more details about the microstructure formation and also about how can we control, how can we manipulate the microstructure. And in the end, I will finish with some outlooks and future work. Okay, so maybe you remember from the presentation on Monday, Christian Weinenbach, what these shape memory alloys are. So shape memory alloys is a class of smart materials that have the ability to recover the original shape after being deformed. So this is our very first sample that we fabricated at EMBA. So it's a very simple bars produced by LPBF, and here the bar is banded. Then if we go with the heat source, the bar goes back straight, so goes back to the original shape. The mechanism that is responsible for this shape recovery is mainly a phase transformation. So when we apply a stress, we induce a solid state transformation from a high temperature phase, austenite, to a low temperature phase, martensite. So this is what we are inducing by deformation. So now the bar is deformed and we are here. So we have a martensitic sample. Martensite is not stable at high temperature. So if we heat the material above a specific temperature, the so-called austenitic finish temperature, the martensite tend to transform back to austenite. And with this back reversion, with this back transformation, our system goes back to the original configuration. And we have the shape recovery. This is what is defined as shape memory effect. And one thing that we need to keep in mind is that the shape memory effect strongly depends on the microstructure. Microstructure means phase fraction, means grain size, but also texture. So now maybe it becomes clear to you why we want to go for LPBF. So laser powder bed fusion is this technique that allows us fabrication of parts that are complex. So we have these intricate geometries that we can fabricate, we have no limitation in the design. But in addition to this, laser powder bed fusion also allows to control the microstructure. So if we play with the processing parameter, we can really change, we can really tailor the microstructure of the part. So now, if we think about combining the shape memory alloys with laser powder bed fusion, we are able to produce part whose functionality, whose shape memory properties can be tailored, can be manipulated based on the application that we want. And this is exactly our final goal of this study, of this project. So how do we start? We start always with the standard parametric study. So we start from the powders, the composition is up there, and we do this design of experiment where we produce very simple cubes with different processing parameters. And the idea is always the same, so find a parameter window, so a range of volumetric energy density that give us dense part, so without cracks and without pores. Well, what I can say is that already this first stage, we start realizing that maybe this is a perfect material for microstructure control. So we are probably working with the right alloy in order to apply this possibility of microstructure manipulation that is offered by laser powder bed fusion. Well, why can I tell you that? Well, if you look at the microstructure of sample, you can really see that we have the possibility of fabricating completely different microstructure simply by changing the volumetric energy density. And in particular, simply by changing the scattering speed. So we can really have samples which are completely different in terms of texture, in terms of phase fraction, and also in terms of grain size. So let me explain a little bit in more detail how can we get and why can we get such a different microstructure. So if we look at the chemical composition of our alloys should be austenitic. So should solidify as austenite. And this is what we see in the case of low volumetric energy density. So we have samples which are fully or almost fully austenitic, and we have the typical long grains elongating along the ring direction with the 001 texture. So what we can expect from an LPBF sample. But if we go to the case of high volumetric energy density, the microstructure changes completely. So we have a sample which is a mix, it's a dual phase sample of austenite and ferrite, and the grains become very fine and equiaxial. And the texture also change. We have a 101 texture along the grain direction. So why we have that? Well, if you think about what does it mean high volumetric energy density? High volumetric energy density means that the heat that we introduce in the material is very, very high. And this in extreme case of high volumetric energy density, the heat input is so high that part of the manganese can be evaporated. So we have a loss in the manganese during the process. So basically what we are doing here is we are changing the chemical composition of the alloy. And this is a crucial point, because the chemical composition is what defines the phase stability. The chemical composition is what affects the primary phase that forms during solidification. And if we think about it, manganese is an austenite stabilizer. So with this loss in manganese, we are basically changing the primary phase of solidification from austenite to ferrite. So this is why we have a high amount of ferrite in the sample after fabrication. But there is even more happening during the process, because as we know, LPBF is a layer-wise process. So the layers that are already solidified, that are already consolidated, can be reheated. So they can experience the so-called intrinsic heat treatment. And this intrinsic heat treatment is responsible for a solid state transformation from the primary ferrite to austenite. And this solid state transformation leads to grain refinement, but also leads to the formation of this specific 101 texture, because there is a very strict orientation relationship between the primary ferrite and the transformed austenite. So much about that, so many information. What we can say here to summarize is that by playing with the volumetric energy density, we can really change the amount of manganese that evaporates. And we can use this to change, to modify the microstructure. So this, let's say, is a first strategy that we can use as microstructure manipulation. But we went even further, and we played also with the scanning strategy, in particular with the rescanning. So rescanning means that we have the powder is scanned for the first time, and then, before depositing again the powder, we rescan again the same layer, completely or only in specific area, only specific location. So here we can well imagine that the situation is very similar to the high volumetric energy density case, because the manganese evaporation is enhanced, is promoted. We have a first manganese evaporation with the first scan, plus an additional manganese evaporation with the second scan. And so what we are doing again, we are losing in manganese, so we are stabilizing the ferritic phase, and the result is here in this slide. So we can really change from a microstructure which is fully austenitic or a mix austenite-ferrite to a sample that is 100% ferritic. So this again is another strategy, let's say, that we can apply for microstructure modification. So here are two examples where we apply these two different strategies. So in the first case, we could build a kind of a chessboard sample where we alternate the volumetric energy density. And the result is really a sample that combine area 100% ferritic with area 100% austenitic. Here we apply instead the rescanning. So we could transform a sample that was originally austenitic in a sample with some specific region of ferrite. So the nice thing here is really to see that we have a fully control of the microstructure. So with this laser parameter, we can really integrate in a single sample completely different grain size, completely different phases, and also completely different texture. Okay, but how can we use that? So is this only nice to produce this colorful EBSD map? Well, there is much more that we can do with that. Because if you remember from the first slide, I said that the shape memory properties, but also the mechanical properties, strongly depend on the microstructure. And here is an example already shown by Christian, where we can see that with the high volumetric energy density microstructure, we can really improve the strength of the materials. Okay, but we gain in strength, but we lose in shape memory properties. The shape memory properties can be increased with the microstructure obtaining a low volumetric energy density. Here the shape memory property increase a lot, but it's again a trade-off, because we gain in shape memory property, but we lose in strength. So now here we have this idea, so why don't we combine these two microstructures in a single component? If we are able to do this, we can think about fabrication of kind of composite materials that show a good combination of strength, but also good shape memory properties. And how can we do this? Well, we can do this by, again, play with different volumetric energy density, but we can do this also by playing with the rescanning. So we can rescan specific area of the sample. And the nice idea behind is that if we change the amount of area that we rescan, we can really play with the amount of phases that we have. We can really change the amount of austenite and the amount of ferrite. We can really change the amount of fine and coarse grain in our sample. So we can really tune the mechanical property, but also the shape memory property of our materials. So again, if we want to gain in shape memory properties, well, in that case, we will try to increase this area, this type of microstructure. But by rescanning some small area, we can also increase the strength of the sample. If instead we are more interested in the strength, then we will increase the rescan area. So we will increase the amount of ferrite at the expense of the austenite. In this case, we will have high strength, but still some shape memory properties. So this is exactly where we are, and this is exactly where we want to go also as next steps. So they say 3 minutes left, so let me conclude. So what I can say is that we can really show that we have a fully control of the microstructure for this iron-based shape memory alloy. So the microstructure can be really changed locally and site-specifically according to what we want. So this microstructure tailoring can really be used to tune the mechanical and shape memory property of our parts. Well, this seems to work very well with our shape memory properties, but it's something that can be really extended to our materials that contain manganese or other volatile elements. For example, I have in mind this high manganese steel, whose chemical composition can really affect the trip, the twin effect, the work hardening, and the mechanical properties. So still a lot to do, but for now, thank you for your attention, and if you have questions, feel free to ask.